you everyone for coming. This talk is about computing Equilibria in matching markets. This is joint work with my advisor, Tardos, and Saeed Alaei, who is doing the course at Google. So one of the main motivations behind this talk is the school choice problem, where you have a number of students and a number of schools. And each of these students have some valuation for different schools. And each school has some number of available chairs, and obviously each student also wants exactly one chair. So what we want here is to find a mechanism, a randomized mechanism, which is interim and free, which basically means that the student prefers his own value, his own allocation over everyone else. And also we want interim parity efficiency, which basically means that there's no other allocation which is at least as good for everyone and is strictly better for at least one student. We want, obviously, to assign one seat to each student exactly, and in this setting, it does not make sense to have monetary transfers, so we want so let's formalize this a bit more. In our model, we have n unit demand agents with m items, and the value of agent I for item j represented by Vij. And also we have some availability for each item, which for item j is Cj. And for simplicity in this talk, we're going to assume that the total available items is equal to the number of agents. And our goal, as I said, is to find allocation of items to agents so that it's NB-free, it's parity efficient, and assign exactly 1 unit of items to the agents. So what are some known mechanisms for this type of problems? First simple mechanism is serial dictatorship, which tells each agent one by one to choose his most preferred seeds in this school, and moves on to the next agent. This mechanism is parity efficient with ordinal preferences, but it's not NB-free. It doesn't work with cardinal preferences. Also, one simple extension of this mechanism is random serial dictatorship, where at first you fix a random order over the students, and then run serial dictatorship over the random order. This mechanism is also ex post parity efficient, but again not NB-free and not interim parity efficient. Another mechanism is probabilistic serial. Probabilistic serial is NB-free and parity efficient with ordinal preferences, but does not have these properties with cardinal preferences, which is the topic of this talk, or what we want in this talk. So one tool that we use is the market Equilibria. So let's start with a simple case of linear Fisher markets. So in linear Fisher markets, again, we have some agents and some items and some availability for these items. But here, every agent has some budget BI. Every agent I has a budget BI. And wants to maximize his or her utility given the budget constraint. So here, P is a vector of prices, which I'm going to use in this talk, and Xi is the allocation of agent I. And for the case of linear Fisher markets, this utility is basically the dot product of the allocation times the value of the agent, given the budget constraint. So how are the Equilibria of Fisher markets are defined in this linear case? So a price vector is equilibrium if and only if there exists an allocation which is optimal for every agent, given the optimization problem that I just showed you. Also clears the market, which means that every item is fully sold and all the buyers are fully spending their money. So how do we achieve our goals using market Equilibria? For satisfying NB-freeness or guaranteeing NB-freeness, we just give everyone 1 unit of fake money. So basically 1 unit of credit to every student. And also for parity efficiency, we use this and some other thing, which is called matching constraint, which satisfies the unit demand property of agents. But for that, we cannot use this simple linear Fisher model, so we need to add some additional constraints. In particular, let's look back at the utility of each agent in the near Fisher market. We're going to add one additional constraint, which basically means that that agent, this is for agent I, so agent I will get at most 1 unit of items. We call this modified market the matching market. This simple constraint makes the market a lot weirder. And in particular, the gross substitute property doesn't hold anymore, which basically means that there are cases where if you increase the price of a single item, the agent's demands for that item increases. So you might ask, why are you using this? Why aren't you using something simpler instead of this matching constraint like free disposal, in which each agent can get more than 1 unit of items, but should keep the most valuable 1 unit of items and remove everything else. But this does not guarantee the properties that we need. And let me show you an example that illustrates this point. So we have 2 agents and 2 items. Agent 1's value for the first item is 2, and for the second item is 1. And agent 2's value is 0 for the first item and 1 for the second item. If you put the price half for the first item and 1.5 for the second item, and give all the first item to the first agent and a third of the second item to the first agent also, and also give the 2/3 of the second item to the second agent, this will be equilibrium in free disposal utilities. But as you can see here is that the 1/3 of the second item that the first agent gets will be removed. So if the agent would give it to the second agent, everyone would be happier. So this is not Pareto efficient. And also, this is not an equilibrium for our matching markets. But however, we show that the utilities that I just showed you can be represented as some piecewise linear and concave functions. This is how we do that. But I'm not going to go into details of this. But the only thing is that the second term makes it so that if agents get more than 1 unit of items, their utility will decrease, strictly decrease. And this makes it so that this function is not monotone. It's also not separable. So let's talk about some of the related work for computing equilibria in this, for this particular market. This market was introduced in '79 for the application of assigning positions to applicants. The first initial results were an existence of equilibrium proof, also an approximation solution, like a exponential time algorithm that achieves approximation solution. And in general, we don't have a hardness proof for this particular market. We don't know how hard it is to compute the equilibria in general case. But in general, adding more constraints to linear equilibria, market equilibria, usually makes the problem really hard. And the most relevant paper to ours in terms of techniques is the Devoner and Conan paper in 2008, which showed that for the case of fixed number of items, you can find equilibria of the case where you have fixed number of items in polynomial time, and also for PLC inseparable case where you have fixed number of agents, you can also find the equilibria of the market. But our case is non-separable, so this doesn't apply to us. And our result is, first, we show that for fixed number of agents, you can find, or we present an algorithm that finds the exact equilibria of the market in terms of geometry, not the term exact is a geometric term. And for the case of fixed number of items, we give a simpler algorithm that is tailored for this problem. But from now on, you can assume that we are in the first case. I'm only going to talk about the first case where we have fixed number of agents. So what is the blueprint and general idea of this algorithm? We've basically searched the space of optimal utilities of agents to find equilibrium points. And in order to do that, we need some tools. First of all, we need a tool that lets us search this giant space. And also, we need some characterization of the equilibria so that if we found equilibrium points, we realize that we actually found them and we don't skip them. So the first tool that lets us search this space is a cell decomposition tool. So let's start with a toy example that gives you some intuition. You probably have heard this problem before, which is basically how many regions do n lines create in a 2D plane? And the answer is order n squared. And the first time, probably when you heard it in high school, it was surprising that it's not 2 to the n. We basically call each of these regions a cell. And in each point in this 2D space basically fixes the sign of some linear inequalities, which basically represent each of these lines. So each line is a linear formula with only two variables. And more formally, each cell makes a sign of all of these formulas the same. All the points in each cell basically makes the sign of each of these inequalities or formulas the same. This simple idea has been generalized. In particular, when you have m number of variables instead of 2, and you have n number of polynomials instead of some simple lines with degree at most d, it has been shown that you can enumerate all of the feasible cells in a running time that is this much. The only thing that I want you to look at here is that when the number of variables is fixed or constant, this will run in polynomial time. Here, because we want to find it from market Equilibria, it would be really nice to have prices for variables that represent the prices when we want to use this tool. But we can't afford that many variables because the number of agents is fixed. The number of items can be arbitrary. So instead, we search the space of optimal utilities, and we define polynomials in a way that they tell us whether in each cell the values correspond to an equilibrium. Another tool that we use that lets us characterize the equilibria is a bundling tool. So let's say we have an allocation, equilibrium price vector P and an equilibrium allocation X. Since we know in equilibria everyone exactly spend 1 unit of money and get exactly 1 unit of items, we can bundle items in the following way. So basically, if an agent gets some amount of an item whose unit price is more than 1, you should also get some other item whose unit price is less than 1 to cancel it out. And using that, we can define pairs of items as bundles and define alphas for them so that the unit price of the bundle of the pair of items is exactly 1. And using, again, these alphas, we can define the values of each agent for each of these bundles. We call the highest valued bundle of items for each agent the optimal bundles of that agent, which is these bundling will make sense a bit later on. And we also in the paper we show that you can rewrite the allocation of items to agents as allocation of optimal bundles of agents to agents. So let's go to the first to the algorithm that I want to talk about, which is a fixed number for the case of fixed number of agents. I'm not going to go into too much detail, but I'm just going to give you some ideas, and hopefully it will make you interested to read the paper. So as I said, we can't define prices as variables, so we define optimal utilities of agents in Equilibria as some variables. And by adding some linear formulas in our machinery, we can know where exactly this optimal utility is when you sort the value of the one single agent for all the items. And basically, by adding those linear formulas, in each cell, the information will tell us where this point is. And by using that, we define some candidate bundles, which basically pairs the items that are left side of this with the items that are right side of this. But the thing is that these will be defined for each agent differently. And also, we don't know what is the unit price of these bundles. And we need that in order to figure out whether these candidate bundles are actually optimal for each agent. So the next problem will become, what are the prices of the items? And in order to do that, first of all, we brute force and assume that we have a single item for each agent that we know it's in his optimal allocation. And by fixing that and defining a variable for the price of that item for each agent. We only add constant number of variables, but we show that by doing that, we can actually formulate the other prices of all the prices of all other items. How do we do this? We basically use the alphas that we had from the candidate bundles to make each agent propose a price using his optimal value and the alphas for his candidate bundles, propose a price for every other item. And 2 steps would be enough for each agent to propose a single price for every item. And we also show that in Equilibrium, you have to choose the highest proposal between all the proposals of agents to be the price of that particular item. So by adding some polynomials which represent these prices, we know what would be the formula that represents the price of each item, only using constant number of variables. Now that was the first step. I'm going to be even vaguer for the rest of this. The next problem would become, now that you have optimal bundles of agents, whether this market clears using these optimal bundles. And one simple idea is whether you can add the inequalities that you get from Hall's theorem in order to check market clearing conditions, having the agents and their optimal bundles. And the answer is that no, for this case, you cannot do it. For the case of fixed number of agents, you cannot actually add the Hall's theorem. But we actually in the paper show that you can do that for the case of fixed number of items. You just have to use the dual of Hall's theorem. So how do we deal with this problem? The way that we deal with this problem is that we show that for each equilibrium price vector, there exists an allocation which has some nice properties, which I'm going to call a good-looking allocation. And the way that we reach it, again, I want to make you interested in the paper and make you read it. I can't go into details. But the way that we do that is that first we start with an equilibrium allocation and makes agents trade in some interesting ways so that the final allocation has some interesting properties. And by using those properties, we can look for this particular allocation instead of any random allocation that can be represented with only constant number of variables. So what do we do when we found a cell? We get a point from that cell and take a point from that cell and find the prices of items using the polynomials that we defined to formulate these prices. And then having the prices, we just have to solve a linear system of equations to get the equilibrium allocation. And that would be the big picture of this one algorithm. And so let's talk about some of the future directions. One problem is how hard this particular problem is, or whether you can solve it for any number of agents and items. Another problem is, can you make these algorithms that I confess are impractical, more practical and simpler? And finally, can you extend these techniques for the case of general PLC utilities when the number of agents is fixed, which is still open, at least for the case of non-monotone utilities. So that would be it. Thank you very much.